Good day. Welcome to our webinar presentation sponsored by C-Therm Technologies. My name is Adam Harris, CEO for C-Therm Technologies. We're a partner of Rigaku. We are the representatives of the Rigaku thermal analysis and calorimetry product line in the US. Very pleased to feature some of the innovation that Rigaku has been driving in this area of thermal analysis over the past several decades. We're going to touch on the sample observation capabilities available in thermal analysis as developed by Rigaku. My name, Adam Harris, again, pleased to welcome you to our event. I'm the warm-up act. I'm going to be introducing our subject matter expert, Megan Fielding. She's a product manager here at C-Therm that specializes in the Rigaku thermal analysis product line. And really pleased to welcome her here shortly to the discussion. I'll just provide a little bit of background info on C-Therm Technologies and who we are. Looking at the list of those online with us, I see folks from all over the US, some folks from Europe and further abroad as well. Welcome to our presentation. Great to have you online with us. One of the nice things about these webinar events is we can bring folks together in this niche field of thermal analysis that we're involved in, but pull from all over different parts of the world. So I'm grateful to have you online with us. So I see some folks are less maybe familiar with us, and some are certainly very familiar with who C-Therm Technologies is, but maybe just a little bit of background. Our specialty is thermal conductivity. If you were online a little bit early for the presentation, you would have seen a short video on the Trident thermal conductivity instrument. Our raison d'etre in life, our purpose is all about simplifying thermal conductivity testing, largely for developing new composites or materials for the future, for tomorrow. We serve a broad range of industry from electric vehicle producers, polymers, composites, textiles, electronics, explosives, oil and gas, really broad range of industry and application. But our reason and value add is all centered around the thermal property characterization, specifically thermal conductivity. I'll talk very briefly a bit about that background, as we do have a lot of lap over with some of the calorimetry and thermal analysis applications. And we're really pleased about the announcement that we made earlier this year, a new partnership launched with Rigaku, representing them in the US market. Really excited about this opportunity. We've been working with Rigaku for, I think, close to 20 years, and really excited to take this step and help introduce some of the new capabilities that they've been advancing in thermal analysis over 20, 30, 40 plus years. So very exciting time for us here at C-Therm with the new partnership with Rigaku. So I'll just maybe speak very quickly to our capabilities with thermal conductivity. So we launched a new product just prior to the pandemic. It's actually done very well, despite the challenges of launching a new product during a pandemic. The Trident thermal conductivity instrument. It brings together the three most prominent methods for thermal conductivity. The MTPS single-sided sensor, which you see in the lower right of that pyramid-shaped controller, that's a patented innovation by C-Therm. It's a single-sided method. It's the only one that has guard ring technology for ensuring unidirectional heat flow, which is so important to measuring thermal conductivity and thermal effusivity, which we can measure directly with that sensor. The simplest and easiest method to use by far, excellent reproducibility. This is a very significant innovation in the space of thermal conductivity. The probe in the middle is a classic method, a needle probe, transient line source, very robust, nicely complementary to MTPS, and it's really good for sticky samples. If you're dealing with polymer melts, for example, it's a great solution. And we just introduced a high temperature version of this for applications on polymer melts up to 300 degrees C, and also offering a pressure cell up to 2000 PSI. So if polymer melts are of interest, that's a great option. And then the Flex TPS, all about flexibility in the operation of it. You're given more control over the regression analysis. This is really meant for more advanced users, but gives you the power to tackle anisotropic materials, thin films, some more advanced type of material sets to characterize from a thermal conductivity perspective. So the combination of those three methods, all available on a common platform, really speaks to the value of Trident. And that's nicely captured by this statement from Abraham Maslow, just talking about that bias that we have when we only have one solution to present to a problem. When all you have is a hammer, everything looks like a nail. And this is really capturing nicely the sentiment behind the value proposition to Trident. To have a variety of options in thermal conductivity is very important, as the solution for testing really insulative materials is sometimes different than the solution for testing conductive materials or fluids, anisotropic materials, thin films, and so forth. You really need more of a toolbox type of approach to the measurement. There is a nice method selection guide available to assist in understanding the method selection, which is probably the most important aspect of running a thermal conductivity measurement. I would advocate is just getting the method selection right. So there's a free guide available there. It's a free resource. I think it's a 50-page document. It goes through theory and operation, also gives suggestions for where certain methods are best applied, and makes it really a very strong resource in helping you map the appropriate method selection. I'll end just my section with a couple quick comments from some existing clients. Jose Fonseca at Covestro, just commenting on the use of the instrument, very fast, accurate capability to test thermal conductivity. Now they've started out with MTPS, and then they also added the TLS needle to their solution. There is a link available that'll ask Anna to drop in if she hasn't already. Yes, she has dropped in the link to the testimonials. Gives some great coverage on what a customer experience is like with C-Therm's thermal conductivity product line. So as I introduce Megan, I want to just talk a little bit about some of the partnerships we've developed over the years. One of the great opportunities in working in thermal conductivity is we've also developed some very strong relationships with other complementary instrumentation vendors and suppliers. We are typically aligning ourselves with instrumentation vendors that are driving significant innovation in the market. So leaders in the field of their instrumentation, offering technically differentiated instrumentation. We're not interested in offering the copies of other instruments. We're really looking for significant technical innovation of where we can drive new capabilities in terms of material characterization. So one of those examples is Metrovib, which is a world leader in DMA, dynamic mechanical analysis. They have one of the stiffest frames available on DMA, which offers the users the opportunity to have a really broad range of frequency they can test at, high frequency, high force capabilities. They have a really cool robotics platform also available for quality control applications or high throughput labs. You get a sense of what it looks like on screen there, but I really encourage you to check out some of the videos if you're interested in DMA. Very advanced capabilities available from Metrovib. And then really getting to the topic of today, we're going to be focused on thermal analysis and calorimetry, and this exciting new announcement, this partnership with Rigaku as they expand into the US market in their thermal analysis and calorimetry offering with the support of C-Therm. So today we're going to talk a little bit about some of that innovation. We're picking a really specific area of sample observation, and we'll touch on some of the other product capabilities that they offer in calorimetry and thermal analysis. So without further ado, I'm going to stop sharing my screen and invite Megan on screen. Megan, great to have you with us. Megan Fielding, an expert in thermal analysis, calorimetry, product manager for the Rigaku product line in the US. Really pleased to have you online with us, Megan. Why don't you take it from there, and I'll rejoin you for the Q&A session at the end.
Awesome. Thank you, Adam. Thanks for that great introduction. And I'm going to start sharing my screen here. Awesome. So thank you so much, everyone, for joining the webinar today. I am really looking forward to introducing this sample observation calorimetry capability in the US. Let's get right into it. Okay, so let's start off with the basics. Calorimetry, what is it? So there are a few different techniques under the calorimetry kind of umbrella here that I'll mention. So to start, DSC or differential scanning calorimetry and DTA, differential thermal analysis, are techniques that measure the temperature and energy changes due to the endothermic or exothermic reactions that occur as a sample is heated or cooled. You can see an example there on the screen of a DSC measurement with a couple endothermic and exothermic reactions there. Next, TGA is a method where the sample's change in mass is measured continuously during heating, cooling, or temperature hold. And finally, STA, simultaneous thermal analysis, measures TGA coupled with DTA or DSC, so you can correlate mass loss to the heat events. And a variety of properties can be measured with calorimetry, and those are listed on the screen there. They include heat capacity, glass transition, uh, enthalpy of transitions, phase changes, and also thermal stability. With that DSC curve there on the screen, it can be difficult to analyze sometimes. Maybe if you're newer to the technique, or if you're maybe measuring a newer sample and aren't quite sure what all these heat events mean, it can be confusing. That brings us to the next slide. There are some limitations to calorimetry as is in most labs. It can be very confusing, like I mentioned, to analyze the heat events. You're not exactly sure what's happening during these exothermic and endothermic reactions. Is it a phase change? Is it dehydration? Is it a crystallization? Like I said, it can be very confusing. And what amplifies this is that we cannot see the sample. We can't see if it's melted. We can't see if it's change shape, change color. If you wanted to see the change in the sample, you would have to stop the measurement, cool the sample down, and remove the sample. And this would not be very efficient, obviously. If the sample underwent a reversible reaction, it would just reverse. So basically, with the limitations of calorimetry, as most of us are aware, you cannot see the sample. Additionally, you cannot observe the ignition temperature or fluidity, as these are not technically reactions. So all of these reasons have led Rigaku to kind of try to tackle that and create the sample observation technology on their DSC and STA. So this will allow you to see the change in shape and color. All the visual information will be linked to the data for very easy analysis. And as you can see on the screen there, in those red circles where the cameras would be located on the STA on the left and the DSC on the right. The sample observation on STA is available from room temperature all the way up to 1000 degrees Celsius, and on the DSC from -70 to 350 degrees Celsius. Okay, so here we're just going to take a very quick look at the STA sample observation camera and basically how it is configured. So in the furnace, the heat insulating material and the heater bobbin have a window so the sample can be recorded by the camera. The protective tube which surrounds the sample is actually made of quartz, and there is a devitrification plate or a glass plate that protects the quartz furnace from contamination. You can still test in your inert atmosphere or in your air atmosphere. This will protect the sample from the off-gassing. Any measurements can be run, so inert gas or air. Okay, so let's take a quick look at the software for this Rigaku sample observation. So on the left, you can see a typical STA graph. You would see the TG or the mass loss in green and the DTA in blue there. However, the benefits to this software is that you can also see the sample in that sample observation kind of window you see on the right there. So there's always going to be the time and the temperature on the sample video. So you can always correlate it. It also has the TG and DTA data, as you can see there. So as you analyze the data, you're able to kind of watch the video play through at differing speeds. Another way that you can use the software is to input images on the graph. So this is actually trehalose dihydrate in its dihydrate form, and then switching to its anhydrous form, and also with combustion occurring at the end. So these sample observation images are automatically saved in JPG format, Like I said previously, the time and temperature is printed on each image, so you can easily correlate. And since these images are automatically saved, you can easily input, this is just an image of the software, but you could also input them in a Word document or maybe in a PowerPoint presentation, or if you're going to a conference, you could present the data and have these images on the graph just as visual aids. And one more way that you can use the software, very helpful, is to, on the left there, you see the sample image at 26C, which is room temperature. And on the right, that would be the video that you could play all the way through. So you can always have a sample on the left to kind of compare to how it started and see how it changes as it goes through the ramp. Okay, so we are going to start with a couple applications on the DSC Vesta. This instrument, as you can see on the screen, has a smart loader on top. That's an automatic sample changer. So up to 24 samples can actually be added to this instrument, and it will just run through them. This also does have a refrigerated cooling unit attached, as you can see coming out. With this refrigerated cooling unit, you can go to minus 90 degrees Celsius. The actual temperature range of the instrument, maximum temperature range would be minus 170 to 725 Celsius. So with this instrument, it has a very fast cooling rate from 725 C to room temperature in just 8 minutes, which is quite a bit faster than a few others that we've seen on the market. And the range that you can use this instrument for sample observation is negative 70 to 350 Celsius. Okay, so we are going to get into the first application here for the DSC. This is an application of an erasable pen, just on a little piece of paper there. If you know how these pens work, you probably won't be surprised, but let's watch as we heat this sample and then cool it back down. Okay, as we heat there, we see the R, which is written with the erasable pen, we see it disappear. And now we've begun cooling the sample back down. And we see it reappear. Okay, so that's one way that you can look at the data, analyze it. Like I mentioned previously, you can also input the images on the thermogram there. So we see an endothermic peak around 59 Celsius. We see the exothermic peak around negative 32 degrees Celsius. So in the first reaction, we saw the R disappear, and then we saw the R reappear at the end. So this is typically achieved by using the rubber eraser on the back of the pen to create frictional heat. And that is why you would see it disappear. Okay, so our next application here, also using the sample observation DSC. This video is nicely annotated, so here we see the sample in crystalline phase. Okay, now we begin cooling the sample back down. Okay, and now we see that graph with the images input. This is just an example of how you could present your data at maybe a conference or a presentation, using the visual aids to show what the sample looks like before and after each of these thermal events. Just makes it quite a bit easier for people to understand what's going on with the sample, where the melt is, where the crystallization is, and things like this. Okay, so the next instrument we're going to go to is the STA 8122. So as I mentioned, the STA combines TGA and also DTA or DSC. So this instrument has a horizontal differential triple coil balance. It's very accurate and very precise. It's available up to 1500 degrees Celsius, but the sample observation model, which is what I'm really going to be focusing on today, can run from ambient to 1000 degrees Celsius. Also has a great cooling rate, 1500 C to 50 C in just 18 minutes. And the auto sampler is also available on this instrument with up to 24 samples. Okay, so the first application we are going to go into for STA is copper sulfate pentahydrate. You see on the left two images. The image in blue is the sample before it went through this ramp. The image in gray or on the bottom is after the entire ramp. So basically, this is what you would see. You would see the blue as you put it in, and you would see the gray as you took it out. But you might be wondering how it gets to that. Is it an instant point? Is it gradual? You wouldn't be able to tell. So with sample observation, we will be able to watch and see how this happens. Okay, so copper sulfate pentahydrate dehydrates in 3 steps. The first 2 steps, you can see about a 14% mass loss. This represents two water molecules. So it's lost 2 water molecules in the first mass loss, 2 water molecules in the second mass loss. And you see that third mass loss, which is coming up about minus 7%. So it's losing the final 1 water molecule. Okay, so after the third mass loss, we see the sample in its final gray form has lost all of its blue color. And just another example here of how we can present this data. We can show it after each mass loss, and we can see that this color change is gradual. Okay, now I'm going to talk a bit about rubber. Rubber is quite a big application area for this type of technology. Additionally, biopolymers is a big one, and I have an application on that coming up. But let's start with the application highlight on rubber and quantifying the amount of carbon black in rubber. So I'm going to start with the image this time and just kind of give a quick annotation. So we started with the rubber sample. You can see on the left, we experienced some mass loss. The measurement is done in nitrogen initially, and you can see on the screen there at 800 degrees Celsius, we actually switched to air. So with the first 2 mass losses, we're seeing a decomposition of the resin in the rubber, and we're seeing a decarboxylation of the calcium carbonate or the filler in the rubber. And then when we switch from nitrogen to air, there we're seeing the loss of the carbon black. So we see about a 23% mass loss when we switch to air, which means the amount of carbon black in rubber can be quantified, and it is about 23% of the mass. Now let's take a look at the video so we can watch this happen. So we can see the image there. It's starting to lose some mass. You can see that it's getting a bit smaller as it it loses its mass. Just want to provide a heads up that as soon as it switches to air, it's a very quick mass loss when the carbon black is removed from the sample. So keep your eyes open there when we reach 800 Celsius and switch to air. Okay, just about switch to the air here. There we go, and you see the sample turn white. Okay, so the next application highlight is a very important one. It's on biodegradable polymers. There's been a huge push in industry lately with global warming, climate change. You know, plastics are not the best for the earth, so we've been trying to find some alternatives with biodegradable materials. Obviously, better for the earth. So we're seeing quite a few new biodegradable polymers being developed. Okay, so with the development of these new biopolymers, obviously they need to be tested and we need to understand their properties. You know, when do they melt? When do they degrade? What temperatures are they safe to use at? So I just want to point out before I start the video here, that little heat event you see around 150 Celsius on the DTA curve there. If you didn't have sample observation, you might just assume that that's some noise. Doesn't look like a peak really. It's quite flat. But when we use sample observation here, you might be surprised to see that this is actually the melt. Start the video. Okay. So we see the melt there. Now we see the sample start to decompose. Okay, so I wanted to bring this quick application highlight on screen just to so you could see that Rigaku's instruments do have some evolved gas analysis capabilities as well. With this example, we are looking at a solar cell measured with TGMS. The powder was heated from 10 degree or heated at 10 degrees C per minute from room temperature to 350 Celsius in a helium atmosphere. So this is just an image actually, but you can see that before the mass loss, the sample was black. After the mass loss, the sample actually is red. So the gases evolved from this mass loss were determined on the right. They're determined to be hydrogen iodide, iodine, and methylamine. Now there are a couple others, but those would be the main evolved gases. Okay, so this application highlight is just so you can see how we would go about measuring the ignition temperature. So as I mentioned in the beginning, it's very difficult to point out the exact ignition temperature of a sample. So let's take a look at how sample observation technology will be very helpful for this. Okay, so we're going to take a closer look there at that second combustion. As I mentioned previously, you can adjust the playback speed of your run. So this is a much slower playback. Okay, so now they're going to give an example of how to analyze the ignition temperature. I will say this software is obviously in Japanese. For US customers, of course, will be in English. So no worries, it will be much easier in English for you to analyze. So basically what we are doing here is just selecting the range that we need to analyze. There, and from that we are able to pick out the image where the sample underwent the firing, and we are able to see the exact temperature. Instead of having to guess where on the peak it happened, we can actually see, okay, this is the exact temperature. Okay, so this webinar is all about sample observation calorimetry, DSC, and STA. However, I did just want to do a very quick overview of the TMA, which is used for thermal expansion. Also part of the Rigaku thermal analysis product line. Does not have the sample observation, but it is a really nice complementary test method that you can use kind of in conjunction with the sample observation. So I'll give a couple examples of that, but just a quick introduction on the TMA. This is actually the first of its kind in differential TMA. There are many different measurement methods available depending on what property you need to know. There's compression loading, most common. This is how you would find the CTE of your sample. However, if you're working with thin films, there's also an option for you there with tensile loading. Additionally, penetration method is available, and that would help with glass transition or softening temperature, as well as 3-point bending. This instrument has a huge temperature range. It's one of the really nice benefits of it. It can go as low as 150 C. It can measure up to 1500 degrees Celsius. Okay, so let's take a look here at a measurement of PET, actually done with all three instruments, so DSC, STA, and the TMA. So in the TMA there, it's actually the top curve. We can see a sudden increase correlating to the glass transition temperature at around 80 C. During the glass transition, the sample is soft and rubbery, and since the load is being applied to the sample, you can see a large shrinkage there. So for the DSC, we can also see the glass transition, and we can see the exotherm there as crystallization, where the sample slightly expands at crystallization, as you can see on the TMA curve. So testing with DSC, STA, and TMA is important for a polymer such as PET. So you can fully understand the material properties for processing and also for use in products, in addition to the manufacturer's data sheet, of course. Excuse me. So for thermal expansion, just as a quick example, this is a key property that really needs to be understood so the system can account for changes in dimension due to temperature. So, if you're using this polymer in something that heats up, other parts of the system need to be able to account for the change in size in the polymer so that cracks and also failure can be avoided. Glass transition is also a very important property as it will determine the temperature conditions in which the material can be used. It might not be desirable for it to be used in its soft rubbery state, for example. DSC is also a really great tool to test for thermal history, which is especially important in polymers because thermal cycling should be tested on your polymer so you can determine its resistance to thermal aging and also degradation. So let's look at one more example here. So this is a PLA plastic straw analysis, again by all three methods. This is a sample observation video. So just a quick, reasoning why this is important for a straw specifically. It's really important to understand how the material behaves with temperature. Some people, need to use a straw when they drink, and they aren't able to drink without one. So they might want to enjoy a warm or a hot beverage. And it's important to know, when does the straw become soft? When does the straw melt? When is it become unsafe to use? Um, in addition to that example, shelf stability is also a very important consideration. So, like I mentioned previously, you can cycle temperature with the DSC and check for degradation and ensure stability of your product. Let's take a look at this quick video here. Perfect. So I love to show these kinds of, overlap to show how complementary these methods are. You can see during a reaction, is the sample expanding? Is it shrinking? How can we correlate and use these three instruments together to gain the most, knowledge of our samples? Okay, and just to summarize here what we've learned. So, with the sample observation calorimetry capability, we can easily see changes in the color and shape of the sample. This has been an issue for a long time, wondering, how is it changing? Is it changing in an instant? Is it gradually changing? What's happening to the sample? There is now no need for guessing what each endothermic and exothermic peak represent. You're able to see it. Um, you can differentiate noise from the heat event, such as a melt below. So in this sample, which was the PHBH straw we looked at earlier, the melt event, which is circled in red there, does not look like a melt event. It just looks like noise. So if you were to analyze this, a large percentage of people, I'm sure, would miss this. And with sample observation, you can't miss it. So you can analyze your data with confidence, really, and just eliminate the guesswork. So with that, I will bring this to a close. Thank you so much to everyone for taking the time out of your busy days to watch this webinar. I really appreciate it and encourage you to reach out over LinkedIn or email if you have any questions. I am happy to provide the applications that I presented today. We also do have some additional applications. I obviously didn't want to make this hours long, but if you have specific requests for a certain field or a certain sample type, I am happy to help. And with that, I will throw it back to Adam.
Excellent. Thank you, Megan. I'll just get you to stop sharing there. Thank you. Perfect. Great job. That was a real delight to sit through and learn more about the sample observation capabilities on DSC and STA. Boy, you can really see how it enhances our understanding of what's really going on with some of those thermal events, and helps enhance the overall characterization of those materials. Really nice job putting together. And that's what this is one of the many reasons we were so excited to proceed and develop further this relationship with Rigaku, who is a real world-class organization, a delight to work with as a partner. The way they're driving this type of technical innovation, very significant, and I think really enhances our experience in a lab, in our material characterization as we look at some of these different opportunities, whether it's biopolymers or carbon black and rubber, all these different interesting application areas. Look, I want to just conclude here. We're going to have a little bit of an opportunity for a Q&A, but I'll just take care of a couple of housekeeping items in transitioning to the Q&A. There is a rich technical resource available on our website, ctherm.com. The tech library is searchable by keyword. You can look up different application highlights, application notes, etc., available on it. There's quite a significant archive of these webinar recordings, which you can review at your leisure. If what you've heard today was interesting, you're thinking, oh, my buddy John would really benefit from this, You can share these links. It makes it a really easy way to access the information, and you can jump around, fast forward through sections if there's parts that you'd like to, focus on more, maybe listen to again. You can back up and do it. So it's a great opportunity. Now we will be doing a deeper dive on the TMA. We had a little bit of a taste of it today, but later in May, the 26th, we will have a webinar really focused on a deeper dive on TMA. And we'll go over the theory and drive through some different application areas that we've been involved with, and some of which Rigaku has produced over the years that just speak to the capability. It's a very nice instrument. We have a lot of experience with this particular model. It's a great product, and we're happy to maybe just speak a little bit more to that in terms of how it can be leveraged in your work. If you're looking to stay current on the fast moving developments that are happening, it seems like every week there's a new announcement or new development. I encourage you to check us out on LinkedIn. You can follow us there. I believe Anna will probably drop in a link to our page on LinkedIn here as well. She's been dropping a lot in. I really appreciate that, Anna. You're doing a great job. But follow us there. It's a great place to keep track of all the developments and thermal analysis, thermal conductivity, etc. So I'd love to have you with us. And if what you learned today is of interest and you're thinking, okay, well, what would a next step potentially look like? Encourage you to express some interest either in the chat box or in filling out the form that Anna dropped in there to receive a quick quote. You can, if we direct it to the Rigaku page, there's a form there you can submit. It's quick. It only takes, I think, like 30 seconds to fill out. And we can get you a quick quote back to you pretty efficiently. Just if you're trying to get some budgetary numbers, or you've got some money left over in this fiscal, you'd like to see if it fits. We can help you with that discussion. Certainly happy to have a discovery call. And what we're keen on understanding is really trying to better understand your application. We have a variety of tools available, and our role, as we view it, is to really help guide you in that process of method selection, whether it's a DMA application or a TMA or otherwise, to help guide that process in terms of how best you can accomplish your objectives and goals. So we're very happy to have that opportunity. So with that said, I think we'll conclude the formal presentation. I'm going to stop the recording here in a few seconds, and we will open it up to a little bit more of discussion in a Q&A context. So if you have any questions, please make use of the chat box. It's a great resource that way. And if you're joining us as recording, I want to say thank you. Also, thank you to our live audience. Very much appreciate your time. I know that time is in short supply these days. Very valuable commodity, and we really appreciate you joining us online. We hope you found this of good value, and we're really interested in any other ideas you have for topics in the future. So if there's something you'd like to hear about more in the future, please let us know either through the chat box or an email. We love doing these educational webinars, really focused on enhancing the knowledge of thermal analysis and the application of it in terms of how it can help in material development. Okay, so with that said, I'm going to stop the recording. Wish you a great day, anyone dropping off here, and we'll proceed with the Q&A.